All right, we're in 10.3 where we're talking about permutations and combinations. Permutations and combinations are counting techniques that come in the form of formulas for a specific type of counting problem that we're going to talk about here. So to get us started, what we're going to do is think about selecting a certain number of objects from a possibly larger set of objects. And we're going to be doing this without replacement. So consider this first example. How many ways can exactly two elements of the set A, B, C be selected without replacement? Now, there's two different ways to interpret what this means, selecting two objects. And really what it boils down to is whether the order of selection is important or not. So here's what I mean by that. If I'm selecting two elements from this set, then I can think of it in a sequential order. I can think of selecting one object and that being my first choice. And then once I've selected that, selecting a second object or element of that set, that becomes my second choice. And because this is a small set, I can systematically list all possible selections. So for example, remember this is without replacement, so we can't select A twice, for example. If my first selection is A and my second selection is B, I can think of that as the pair of letters A, B, where the first letter is my first choice, second letter is my second choice. The other possibility starting with A would be A, C, so that's a second way to choose two elements from this set. Another choice would be BA. And because B is the first choice here, even though I chose the same two letters here that I chose here, when the order of selection matters, BA and AB are going to be considered different possibilities. So these are counted separately. BC, CA, and CB. These are the 6 possible ways to choose two elements from this 3-element set when we take the order of selection into account. So there's 6 possibilities here. Okay? Now, this is a completely this is an example with no real context. We're just randomly selecting letters from a set. But as we'll see as we get through this section, there are plenty of real-world counting problems that mimic this kind of selection process, where we're selecting objects from a set without replacement, and we care about the order of selection. But there's other examples where the order of selection isn't important. So in other words, we don't want to think of A first, B second as any different than B first, A second in those cases. In fact, we would prefer to think of these as just subsets. If I'm talking about the subset of this set here, A, B, we know that set from set theory back in chapter 2, the order that you list elements in a set doesn't matter. So the set containing A, B is the same thing as the set containing B and A. So this list is double counting a lot of possibilities in the event that I don't care about the order that they were selected. So what that means is if I want to determine the total number of ways to select two objects from this set of 3 letters in such a way that the order of selection is not important, then I would eliminate any duplicates in this list. So for example, since A, B, and BA are considered the same thing with that criteria, we would get rid of BA. And AC and CA are considered the same, so we can get rid of CA. And then BC and CB would be considered the same letters, just in a different order, so I can eliminate CB. That takes my list of 6 possibilities down to a list of 3. Okay? These are the 2 types of problems that we're going to look at in this section. Again, it's selecting a finite number of objects from a potentially larger set, in this case selecting 2 objects from a 3-element set, and then we have the 2 possible cases, whether we want to count according to the order of selection or if we don't care about the order of selection. So again, this example we use systematic listing because the set was pretty small and the list wasn't that large. But it's not too difficult to see that if this set gets much larger and if the number of elements that we're selecting changes, then actually trying to list all those possibilities can be very, very impractical. So what we want to do is see if there's a better way to approach a problem like this. And the goal is going to be to derive formulas for these things that we call permutations and combinations. But as a starting point, we want to think about the tools that we already have. We want to think about that fundamental counting principle that we talked about in the last section. So let's do an example that's a little bit harder than what we just did, but the same kind of idea. We want to use the fundamental counting principle to consider the total number of ways one can select exactly 3 elements of the set A, B, C, D, E when the order of selection is considered. Now, I didn't write this here, but we're assuming throughout this entire section, unless it's implied or stated otherwise, that we're always doing these selections without replacement. So when I say select exactly 3 elements of this set, I mean 3 distinct elements. You can't select A 3 times, for example. Okay, so again, rather than list out all of the possibilities, let's approach this in a more efficient way. So if I think about this as a step 1, step 2, step 3 kind of process, since I'm selecting 3 elements, I'd like to think about the total number of choices that I have, or the total number of options for that first selection. So let's call that first choice. How many options are available to me in this set for the first selection? It would be 5. 5 choices, right? A, B, C, D, E. I have 5 possibilities for my first choice. Now, once you've chosen that first letter, remember, we don't get to reuse it. So our second choice will only have 4. I should call these options. Let's call them options. I only have 4 options for my second choice. And that's because I've used one already. And that means there's 4 remaining to choose from for that second letter. Kind of following that same logic, if I want to make my third choice, after I've selected 2 letters already, my third option is not going to allow me to use the 2 letters that I've already chosen. That leaves me with 3 remaining options. Okay, so according to the fundamental counting principle, in order to determine the total number of ways I can select 3 elements from this set, I would use multiplication. 5 choices for my first selection, 4 options for my second selection, 3 options for my third selection. I think of it as a 3-part task, and I multiply. Okay, 5 times 4 is 20, times 3, that would be 60. So there's 60 different ways to choose 3 elements from a 5-element set when the order of selection is considered. Okay, that would have been a lot of listing. You know, that's why I prefer a method like this to listing out 60 sequences of letters. All right, the second example I want to do is going to use the one we just did. So it says repeat the previous example without considering the order of selection. Now let's think about this for a moment. Let's go back to this set, A, B, C, D, E. These are my 3 choices. Let's look at one possible sequence of letters that I could choose from that set. My first choice might be A, my second choice might be B, and my third choice might be C. Okay? Are there other ways of selecting the same 3 letters but in a different order? Of course there are. Let's look at those. So if I still start with A, but maybe I have C and then B, that's another way to choose the same 3 letters, but in a different order. And those are all the possibilities, you'll notice, of choosing the letters A, B, C, such that A is my first choice. Let's look at what it would take for B to be my first choice. B, A, C is one possible order of selection for those 3 letters. B, C, A would be the other choice that starts with B. And then finally, C, A, B and C, B, A are the other 2 possibilities. Notice these 6 sequences of letters are all the possible cases, all the possible ways that I can choose the letters A, B, C from that set when I'm considering the order. Now, over here, when we considered order in this example, if I were to systematically list out all of those sequences of 3 letters, these 6 would each be counted one by one. You know, in that count of those 60 possibilities, this would be 1, 2, 3, 4, 5, 6. However, if we don't want the order of selection to matter, then all 6 of these would be considered the same result because I'm ending up with the same 3 letters. Okay? So these 6 possibilities should be count as one result. Okay? What other, and I'm not going to systematically list all 60. We're trying to see a pattern here. What if I were to look at a different set of letters? What about the letters A, B, D instead of A, B, C? That's a brand new selection of 3 letters, right? Well, if I consider all possible ways of selecting these exact 3 letters just in different orders, then A, B, D is one, A, D, B is one, B, A, D, and B, D, A, D, A, B, and D, B, A. You should be able to verify that those are the only 6. Notice once again, when I have a different collection of 3 letters, and I'm looking at all the different ways of rearranging those letters, again, I end up with 6. I'm going to count that as 1. In fact, any distinct collection of 3 letters from that 5-element set will always have 6 different rearrangements. And we actually know that because the how many ways or how many arrangements, number of arrangements of 3 letters is 3 factorial. We talked about rearranging elements of a set in the previous section, and we showed that however many elements are in the set that we're rearranging, the factorial of that tells me the total number of rearrangements. This is equal to 6, which you can easily verify. That's why we keep saying 6 in each of these lists. So now let's think of it this way. If I were to actually systematically list all 60 of these possible 3-letter combinations, and then group them up in 6s according to which combinations contain the same letters, regardless of their order, then that's like taking that list of 60 and dividing it by 6, because I'm taking groups of 6 and counting them as 1. So that means the total number of possible combinations of letters when order is not considered is the list of 60 divided by 6, which equals 10. Okay? These 2 examples are going to provide the intuition for the more general formula that we're going to use. You're not going to need to do this listing thing. This was just to kind of give you an idea of where we're going with this concept. So let's explore the logic behind those examples in a little bit more depth. Returning to this one, you may notice that when we use the fundamental counting principle to determine the total number of ways of selecting 3 objects from a 5-element set, what we got was something that looks a little bit like a factorial. Think about what 5 factorial would look like. 5 times 4 times 3 times 2 times 1. The problem is that we cut it short. We didn't go all the way down to 1 because we had 5 choices, but we were only trying to fill 3 slots. We were only trying to make 3 selections. So there could only be 3 numbers in this product, not allowing us to get down to 1. It's not too difficult to see that any other problem like this, where we're selecting, let's say, R elements from a set containing N elements, then what we're going to have in a case like that is something that looks like a factorial but doesn't make it all the way down to 1 necessarily. So to make that a little bit more precise, again, we're choosing R elements from a set containing N possible choices. N would have to be greater than or equal to R in order for that to make sense. And for the very first choice, we have a total of N possible choices. Again, our set that we're choosing from contains N elements. So the fundamental counting principle says we're going to multiply some stuff. N choices for that first element. Once I've chosen that first element, I don't get to use it again. So I have 1 less to choose from in my second selection. That's why we multiply N to N minus 1, which is the number that's 1 less than N. Once I've made that second selection and I'm moving on to my third selection, I've now used 2 of the elements in my N element set. So I need to subtract 2 from the original n choices to determine the number of choices that I have for this third selection. And you can see how this kind of creates a pattern that eventually comes to a stop. Now, why does this last factor in this product look like this? N minus, in parentheses, r minus 1. Well, again, remember, the number of factors that should appear in this product should be r. It's just like this. We had five elements to choose from, but we only wanted to select 3 from that set of 5. And that gave us 3 factors here. In this case, I'm choosing r elements from a set of n, so I should have a total of r factors here. Now ignore this n for a second. If I just look at the number that I'm subtracting from n, I have 1, 2, then in between here 3, 4, 5, or however many there are, eventually ending at r minus 1. That's a total of r minus 1 factors. But then when I include this n right here, that's 1 more, bringing me up to r factors in total. Now, I didn't mention this yet. I wrote it up here, but I didn't talk about it. This notation is going to represent these types of problems. We call this kind of a counting problem a permutation. So again, a permutation is a counting problem where we're selecting r objects from a total of n choices, and we want to consider the total number of ways that we could do that when the order of selection matters. And this formula gives it to us. Now, this formula, the way that I've written this, is not very useful, because if r is a large number, then that's going to be a lot of things that we're multiplying here. And so even though this will give us a correct answer, we have a way of simplifying this a little bit. A common technique that we use throughout math is to take an expression and multiply it by another expression that's equal to 1, usually in the form of a big fraction. So again, remember the way that I described this before is that it looked kind of like a factorial, but one that came to an end too early. It didn't make it down to 1. So if I wanted to force this thing to look like a factorial, I need to provide the rest of those factors that are missing here. Remember, we keep subtracting something from n until we get to r minus 1 here. If I kept going, the next largest number that I would subtract from n would be r, and then r plus 1, and so on and so forth. Eventually, we subtract enough things from n to get down to times 2 and then times 1, which kind of completes this factorial. So in the numerator here, these are the factors that are missing from this permutation to make a factorial. But I can't just multiply by that, because I'm changing the value. So I have to create a quotient out of that where my denominator is equal to my numerator. In that sense, I'm multiplying by 1, which doesn't change this. Now, we know how to multiply fractions. This thing gets multiplied up into the numerator here. And this expression, although it looks really, really complicated, is just taking the numbers starting from n and multiplying everything from n down to 1 together. That's the same thing as n factorial. So this big complicated mess up in the numerator really just boils down to n factorial. But what's going on in my denominator? Well, that came from here, and we started in this case at n minus r, multiplied by all of the numbers from n minus r down to 1. That means that we're looking at n minus r factorial. And this is a simpler version of this formula. They're equal to each other, but it's easier to work with this than it is to work with this. This is our permutation formula. Okay, and here it is just stated, without all the work in between. So let's use this example. Well, let's use this in an example, I should say. How many 4-digit numbers can be created using only odd digits? And how many of these 4-digit numbers have no repeated digits? So first of all, what are the choices that we have available if we're only looking at odd digits? 1, 3, 5, 7, 9. Those are the only odd digits. Okay, that's 5 to choose from. Now, this is a 2-part question. Notice the first part says how many 4-digit numbers can be created using only odd digits. Well, one 4-digit number that uses only odd digits is the number 1111. That's 4 ones. In that case, I'm allowing myself to use the same digit multiple times. And so in this case, this doesn't fit the description of a permutation quite yet, because remember, permutations and combinations, we haven't talked about combinations yet, but both of them are assuming that we're doing a selection process without replacement. And this first question is with replacement. So we use the fundamental counting principle for the first part. I have 5 choices for my first digit, followed by the same 5 choices for my second digit, because I'm allowed to reuse digits, followed by 5 choices for the third and 5 choices for the fourth. This is 5 to the 4th power, which equals 625. That's the answer to the first question, and that's a question that we could have asked in the previous section. We didn't need any information about permutations yet. But now, this follow-up question says, how many of these 4-digit numbers have no repeated digits? So that would look kind of like our first example, where I had 5 times 4 times 3, because I keep using up options from this set. But rather than think of this using the fundamental counting principle, let's instead think of it as a permutation. So how can I think of this in terms of a permutation? Well, again, n represents the set that I'm choosing from. I have 5 choices in there. I'm looking at a permutation where I have 5 choices and I want to select 4 digits from that set. 4 goes here, okay? 5 to choose from, but I need 4 to make a 4-digit number. According to our formula, this is equal to 5 factorial over 5 minus 4 factorial. Now, it's really, really important to remember that you don't get the distributive property here. You can't distribute this factorial and say this is equal to 5 factorial minus 4 factorial. It's not. You'll get the wrong answer. You have to do the work in the parentheses first. So this is equal to 5 factorial over 1 factorial. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 1 factorial is just 1. So this is really just the same thing as 5 factorial. If you do the multiplication, this comes out to 120. Now it makes sense that this number should be smaller than this one, because all of the 4-digit numbers that we counted up here will include these ones. Remember, this count includes 4-digit numbers with repeated digits and without them, because it includes all of the 4-digit numbers consisting only of odd digits. So logically, we would have expected this number to be less than this one. Okay, let's try another one. I want to create a code. We did an example like this in the previous section as well. This time it's a 9-digit code, and it has to be chosen in a way such that the first 2 digits are letters of the alphabet, the next 3 digits are numbers from the digits 0 through 9, and the last 4 digits are special characters from this set. Notice this has 6 special characters in it. If the code can't contain any repeated digits, how many codes exist that meet this criteria? Okay, so for us, what we're going to do is think of this in 3 blocks. So the first block, what I mean by block is if you have your code, let me actually give you an example of a code. So if I have my first 2 digits are letters of the alphabet, I'm going to do this down here. One block, or one possibility is that I have AB. Remember, we're not allowed to repeat letters here. The next 3 digits have to be numbers from 0 to 9. So what if it's 0, 1, and 2? That's one possibility. And then finally, I need 4 digits from this list of special characters. So let's just say exclamation point, @sign, $sign, $sign. Okay, this is one possible 9-digit code. But what I want to do is, because we can break this code up into blocks, little pieces, where those blocks choose from different sets. I want to think of this in 3 parts. So the first block, I have letters of the alphabet to choose from. And I know that there are 26 letters of the alphabet. So I'm looking at 26. It's a permutation because it's a code. The order of the letters in this code matter. The code starting with AB is going to be considered different from any code that starts with BA. But I'm only choosing 2 letters for that first block. Okay? How do we evaluate this? This is equal to 26 factorial over 26 minus 2 factorial. Okay? This is equal to 26 factorial over 24 factorial. I did the subtraction first. Now remember what a factorial is. 26 times 25 times 24 times 23 times ... This eventually comes down to this. 24 factorial is equal to 24 times 23 times ... Eventually gets down to 2 times 1. And notice all the cancellation that happens here. All that's left is 26 times 25. Okay? And so in this case, we just get 26 times 25, which is equal to, what is that? That's 650. I think that's right. Just mentally check that really quick. Yeah, 650. Okay, and then we move on to the second block. So for our second block, 3 digits to choose from. Or sorry, 10 digits to choose from, because it's the digits 0 through 9. That's 10 options in total. But I want to choose 3. I want to choose 3 digits from that set without repetition, without replacement. So that's 10 options, and I'm choosing 3 from them. Okay? This would be equal to 10 factorial over 10 minus 3 factorial. Now I'm not going to write out all of this work again. What I'm going to do is do this step, 10 factorial. This would become 7 factorial, right? But rather than write out this big product, I'm going to think of this just in my head. I know that 10 factorial is going to multiply everything from 10 down to 1. But then the 7 factorial down here is going to multiply everything from 7 down to 1. And 7, 6, 5, 4, 3, 2, 1 is going to cancel with the same numbers up here. So that means for my 10 factorial, everything except for 10 times 9 times 8 is going to cancel. Because after that, 7 and onward will cancel with this. This is equal to 720. Okay? And now for my third block. What's my permutation look like this time? Well, we're choosing special characters from this set, and I want to choose 4 of them in a sequence. So that's 6 here, 4 here. This is equal to 6 factorial over 6 minus 4 factorial, or 6 factorial over 2 factorial. Notice, same logic as above. This is equal to 6 times 5 times 4 times 3. Okay? 6 times 5 is 30. 4 times 3 is 12. And 30 times 12 would be 360. Okay? So now for my final answer, because I just got 3 different values here, what am I supposed to do with those? Well, remember, each of these represent a block of this code. And I can think of creating blocks of this code as parts of a 3-part task. So that's where we go back to the fundamental counting principle. If I want the total number of possibilities here, I take the total number of possible ways of choosing the first block, which is 650. Multiply that to the total number of ways of choosing the second block, which is 720. Multiply that to the total number of ways of choosing the third block, which is 360. And if you do this probably in a calculator, you get 168,480,000 results. Okay? This is why we like these formulas. You may have looked at this and thought that felt like kind of a lot of work, and that's only because I'm taking my time with it. Usually this will go faster than even what we did here. But I don't think there's going to be any argument that this process is preferable to systematically listing 168,480,000 possible codes. There's no way that that's a practical way to go about solving this problem. You need counting techniques like what we've talked about here. Okay, we're going to continue this in another video.